I am Mazhar-ul-Islam from University. The topic of my presentation is the improved chemical properties of bacterial cellulose by the addition of SSGO as an additive in chemically defined medium. As we know that cellulose is a polymer of glucose units which are joined together by 1,4-beta glycosylic linkage. It is the chief polymer found in all plants. About 33% of all plant material consists of cellulose. However, plants are not the only source of cellulose. There are certain microorganisms, bacteria, which can produce cellulose by fermentation of different carbon sources. This cellulose is called bacterial cellulose. The chemical structure of bacterial cellulose and plant cellulose is almost similar, as we can see from this image. However, the properties of bacterial cellulose are much superior compared to plant cellulose. You can see certain bacteria strains which produce bacterial cellulose. For example, Acetobacter xylenum, Gluconacetobacter, and other strains, other species of the same genus, they can produce bacterial cellulose. In this our present study, we used the Gluconacetobacter hincinaceae for the production of bacterial cellulose. The general synthetic mechanism of the cellulose by bacteria is that when bacteria are inoculated into a medium which contain carbon sources and some pernicious sources, they go there and these glucose units then join together from glucone chains, and then these glucone chains are excreted out of their body extracellularly, where they combine together forming microfibrils. These microfibrils still combine forming fibrils, and finally ribbons and a reticulated structure of cellulose solid structure is formed at the end. Basic source of cellulose formation is glucose. However, other sources like fructose, hexose, sucrose, etc. can also be utilized. Different media are synthesized for the production of bacterial cellulose, which are the chief needs for the growth and production of bacterial cellulose. In this study, we use a chemically defined media having the following composition. Besides this media, there are many other media, synthetic and non-synthetic media, which can be utilized for the production of bacterial cellulose. For example, we can see a few of them here. This is the basic synthetic pathway of bacterial cellulose. Our motivation for the present work comes from this synthetic pathway. We can see here that glucose is utilized as the chief source for the production of cellulose. This glucose is converted to a series of reactions, reversible reaction to a UDP glucose and another compound. This UDP glucose then can be converted to cellulose by cellulose synthase enzyme, and also the same precursor is used by another byproduct, D-glucuronic acid or D-glucuronic acid oligomers. So our aim of our study was that to inhibit these side byproducts in order to increase the production of cellulose. So to inhibit the synthesis of glucuronic acid, we use the feedback inhibition strategy that we added initially this D-glucuronic acid to the synthetic media, to the chemically defined media, so that the presence of this D-glucuronic acid in the media will cause the inhibition will cause retardation or inhibition of the synthesis by damaging the activity of its enzyme or slow down, retarding the activity of its enzyme. So based on this perspective, we use the following study and we got positive results. This is the structure of glucuronic acid oligomers, simply abbreviated as SSGO. They are water soluble, having their mass less than 1,000, and usually alpha length. They are nice dispersant and emulsifying agents. This is the structure of solid powder form of SSGO. So as I mentioned that these are produced as a byproduct along with the cellulose in the process. So they are removed, they are isolated from the culture broth through following steps. The culture broth is centrifuged So the solid material, they settle down as precipitates, and as these are soluble in water, they remain in the supernatant. Then supernatant is treated with 5 volumes of ethanol, and with ethanol they are precipitated. The process is repeated 2 times to get purified form, and finally then these are dried to be used in further experiments. The results obtained by supplementing SSGO to the media shows that we get the increased production and productivity of bacterial cellulose and improved mechanical strength of BC and higher water retention rate. This is the data when we get the bacterial cellulose in the media which do not contain SSGO. This is the control system. So we can see that the bacterial, when only 1% or 10 gram per liter glucose was used as a basic carbon source, cheap carbon source, the bacterial cellulose synthesis was about 7.4 gram per liter. However, besides this bacterial cellulose, SSGO was also produced. So the aim of our study was to inhibit the production of this SSGO and to increase the production of bacterial cellulose. So in order to achieve the goal, we did another set of experiments by adding SSGO to the media. So here we can see that when SSGO was added to the media, the production of bacterial cellulose was much increased. And we get 10.5 grams per liter of bacterial cellulose with this experiment. And also it is clear that this was the initially added amount, but during the process, no additional SSGO was produced. Besides producing, some of the SSGO was consumed in the reaction. So our first study aimed that this further production should be stopped, that was achieved. However, with this interesting result that the decrease in the amount of SSGO occur when it was supplemented, 1% SSGO was implemented to the media, then we plan to know why this SSGO was consumed. Is it utilized in the production of bacterial cellulose? So to prove this concept, we then did another set of experiments. And these experiments, we only used SSGO as a carbon source and didn't add any glucose. So we can see that still the SSGO was consumed in the reaction, and certain amount of bacterial cellulose was produced. This proved that as production of SSGO is a reversible reaction clear from the synthetic pathway, so some of the SSGO was transferred back to glucose, which are converted into glucose. And also we get certain small quantity of glucose also in the same media which were not initially added to the media. So this shows that SSGO can be utilized as a source for the production of bacterial cellulose. So these studies show that SSGO can be used as addition of SSGO initially to the media can result in a higher amount of bacterial cellulose, and also it can inhibit its self-synthesis. Further, we investigated its physic-chemical properties. So the same images of the BC produced without SSGO and with SSGO showed that the fiber thickness of the BC produced with the addition of SSGO was slightly more. It was a little more thicker, and the thickness of the fibers resulted in better mechanical strength and its water retention rate properties. If we can see here, this is the mechanical strength of the BC produced without SSGO, and this is the mechanical strength of BC produced with SSGO. So the tensile strength of BC produced with SSGO was about 5 times higher, and its Young modulus was about 1.5 times higher than the BC produced without addition of SSGO. And we also analyzed the comparative water retention rate and water holding capacity. We can see that this is the water holding capacity and retention rate of BC produced without SSGO, and this is the BC produced with SSGO. The water holding capacity of both type of BC was similar. However, the water retention rate of BC produced with the addition of SSGO was higher. So this higher water retention rate has much importance in biomedical fields. So we can say that with the addition of SSGO, to the basal media can result in higher amount of BC and also with improved physicochemical properties. So constitutes an important byproduct obtained by BC, and it can be efficiently utilized in the production of bacterial cellulose and has increased productivity and higher physico-chemical properties.